Hello, everyone. My name is Dayan Madrin, and I'm from the University of Novi Sad, Faculty of Technical Sciences, Department of Production Engineering. Today, I will explain how you can use 3D printers and injection molding technology in practical applications, and how to produce a low-budget insert for injection molding dies. I will also showcase different techniques of 3D printing applicable in this field. Many of you are likely familiar with 3D printing or rapid prototyping technology, which is now commonly referred to as additive manufacturing. This change in terminology reflects how the technology has evolved. Initially, it was primarily used to create prototypes or parts with limited mechanical properties, and the surface quality of these parts was often poor, preventing their use in production or final products. However, advancements in this technology have transformed it into a viable production method, enabling many companies to use it for creating final parts and complex assemblies. So how does it work? The process is quite straightforward. It employs a layer-by-layer system where a printing head or laser generates one layer at a time. After the first layer is applied, subsequent layers are added until the final part is completed. To start, we need a CAD 3D model. This model can be created using specialized CAD software or downloaded from the internet. While downloading models can be convenient, creating your own design allows for greater flexibility and editability. Once the 3D model is complete, it must be converted into a specific data format known as STL, Standard Tessellation Language. This format is suitable for slicing the model into layers and exporting it into G-code, which machines use to produce the final part. After production, the part may require post-processing to achieve the desired dimensions or surface finish, which can involve techniques such as sanding or turning. Additive manufacturing technologies are classified into several categories, as shown in the table in the slides. The ISO and ASTM standards categorize these technologies into groups such as vat polymerization, powder fusion, foil lamination, binder jetting, material extrusion, direct 3D printing, and direct energy deposition. The differences among these groups lie in the methods used to generate layers or contours, which can involve lasers, projectors, knives, or printer heads, among others. Each of these technologies also has specific commercial names, with familiar examples including stereolithography, selective laser sintering, and fused deposition modeling. Additionally, each technology has unique abbreviations that relate directly to its functionality. For rapid tooling of instances in injection molding, I will discuss a few technologies that are suitable for the production of inserts. The first technology that can be used is FDM, fused deposition modeling, along with other methods such as stereolithography, SLA, and selective laser sintering, SLS. It's important to note that while some technologies are well suited for this purpose, others may be limited or require additional post-processing. I will elaborate on each of these technologies shortly. FDM is one of the most well-known and popular methods today and is widely available, from home use to large-scale manufacturing systems. FDM is an abbreviation for fused deposition modeling, also referred to as fused filament fabrication, FFF, in some literature. This method is quite simple. It uses filament spools made from various polymer materials, such as ABS, PETG, or PLA. The printer's head melts the plastic filament and, layer by layer, builds the final part. However, this technology has a limitation. When creating parts with overhangs, support materials are required. In such cases, printers typically have two different extruder heads, one for the base material and another for the support material. Fused deposition modeling, FDM, has some limitations when it comes to producing mold inserts. Firstly, regarding materials, FDM can only utilize polymer materials. If you require materials that can withstand high temperatures or high pressures, you will need to invest in more expensive industrial 3D printers. Additionally, the surface finish of the final parts produced through FDM is often inferior compared to other technologies, such as stereolithography, SLA. Consequently, post-processing is typically necessary. In the image on the right side of the slideshow, you can see a red mold insert printed using FDM and ABS material. This insert can produce only a limited number of final parts. To the right of that, you will find white specimens used for tensile testing. We produced over 15 to 20 of these specimens. However, in the lower figure, you can observe noticeable degradation of the insert due to high pressure and high temperature, which has caused damage to much of the material in the insert. For certain applications, like cup testing, where only 10 or fewer parts are needed, FDM proves to be a very suitable technology. The main advantages are its low cost and simplicity. For standard materials like ABS, the price is about 30 euros per kilogram, but producing this insert costs us no more than 5 euros. Moreover, the technology is straightforward, requiring no special preparation for 3D printers. It's also easy to adjust printer parameters, and the slicing software is simple to use. FDM technology is not only limited to producing injection molding inserts. It can also be used to create various parts of dies or tools. On the right side of this slide, you can see a picture of an ejector plate that we produced using FDM technology and a cost-effective material called PLA. We utilized this ejector plate in the tool I presented on the previous slide. The blue and brown ejector plates are different due to variations in their patterns. The production of this ejector plate takes approximately 3 to 3.5 hours, and the amount of material used is minimal. Moreover, the quality and mechanical properties are sufficient to guide the ejector and ensure it directs the final parts effectively. Next, I would like to present a technology known as stereolithography, specifically mass stereolithography. This technology is quite similar to others in the field, utilizing liquid photopolymers. Depending on the specific method, we can employ UV light through projectors or diodes, or alternatively, use lasers. The technology itself is straightforward, and today you can find very affordable devices in the market, along with a variety of polymer materials suitable for 3D printing of injection molding inserts. Typically, these materials are based on acrylate polymers. By incorporating different additives, these acrylates can withstand very high temperatures, over 250 degrees Celsius, and are also designed to endure high pressure. One of the primary advantages of this technology for injection molding is the high surface quality and low roughness it provides, resulting in high-quality final parts produced with these inserts. However, like other polymeric inserts, there are potential issues. Due to the high pressure, some inserts may become deformed, which could lead to material leakage along the parting line. In the market, you'll find various 3D printers, both SLA and MCLA. Their prices can range from as low as 100 euros to several 100,000 euros. The price difference often reflects the printer's purpose. Lower-cost models are generally intended for hobbyists, while those in the mid-range, usually between 10,000 and 20,000 euros, are semi-professional, and the most expensive models are industrial grade. In the next few slides, I will share results from inexpensive commercial hobby 3D printers, which can yield results comparable to those produced by printers costing over 200,000 euros. However, it's essential to understand that expensive 3D printers typically offer larger build volumes and improved materials, resulting in easier operation and greater reliability. One example I prepared for this training is a small coin or badge featuring our project logo. On the right side of the slide, you can see the 3D models of this coin. The bottom of the slide shows what the insert looks like for producing our coin. We used MCLA technology with an ABS-like material, not pure ABS but an acrylic, and we did not perform any post-processing after the 3D printing. We used the printed part in its raw condition. In this next slide, I will present the insert produced by SLA or MCLA. The green part at the bottom of the slide is the insert we produced, which is shown in the previous slide. In the middle, you can see the insert placed within an injection molding machine, specifically an Engel Victory 50 model. On the right side, there is a final part, along with an image from an intermediate stage of the injection molding process, where we had not yet finalized the volume of the molten material. For production, we use polypropylene. As you can see, the final product is not yet fully developed. We will need to perform some fine-tuning to prevent errors related to the ejector. Additionally, the ejecting plate in this die has been produced using FDM technology, And you can see that this die consists of more than 2 parts made through 3D printing. One technology suitable for producing inserts for direct molding is selective laser sintering, SLS. While it's a viable option, post-processing is necessary since the base material is powder. The roughness of the final surface depends on the size of the powder particles, and this roughness tends to be too high. Therefore, some form of cutting or other post-processing methods is required to minimize surface roughness. In SLS, polymeric powders, such as polyamide, can be used, and a laser melts this powder layer by layer to produce the final parts. As previously mentioned, there are various price points for 3D printers, similar to other technologies. However, we don't typically find very cheap options in the market. Generally, quality 3D printers can cost over 50,000 euros. The choice of which 3D printer to use depends on the size of the printer chamber and its working volume, as well as the materials required for the final parts to be produced. 3D printing can be used not only for producing polymer inserts, but also for creating molds. For example, using direct energy deposition, DED, which is akin to welding, we can utilize a wire or powder and apply energy to melt these materials. This allows us to produce molds that incorporate conformal cooling channels for specimens. What does this mean? It means that when we perform simulations to optimize cooling for complex parts with large volumes, we can predict intricate cooling channels. In traditional approaches, we often drill injection molds, resulting in straightforward channels for cooling. In contrast, conformal channels can take on complex 3D shapes, which can be more efficient. There are 2 types of devices used in direct energy deposition, each employing different methods to create layers. One method uses a printer head that spreads powder onto the working table or onto previously produced layers, where a laser beam melts the powder to create the part. The other method involves using a metal wire fed into a device, which also utilizes an electron or laser beam to melt the wire, producing layers layer by layer until a complete 3D part is formed. Selective laser melting, SLM, is another popular but more expensive technique that utilizes metallic powders made from various metals like tool steel, iron, and other alloys. In this process, a laser beam heats and melts only the powder in the zone it targets. However, this technique has some limitations because the metal's weight necessitates support structures inside the conformal channels. This support material can restrict fluid flow, which is undesirable. Ideally, support structures should be designed to be minimal and create little resistance to fluid flows. Thank you for attending. If you have any questions that I haven't addressed during this presentation, please feel free to contact me via email or my mobile phone. I'm also available on WhatsApp, Libra, Telegram, and other social networks. Thank you.